All right, hi everybody. Welcome to ML Mondays lecture number 3. We're going to be talking about logistic regression. But before we go into that, we have an announcement to make. So we actually have HyperGator tours coming up. So we're going to be posting that on our Instagram and on Discord as well. And if you guys don't know what HyperGator is, it's essentially the supercomputer here at UF. So you get to go around basically like all of the GPUs that they have, and they basically explain the history of HyperGator, how it was created, and also how it works. So definitely check on our Instagram to sign up for that, and we'll definitely give you guys more info there. But anyways, yeah, Siobhan is our ML lecturer for today, so I'm going to let him take it away from here. Yeah.
Hi guys, today will be our third lecture on logistic regression. So the previous two lectures were Introduction to Machine Learning and Linear Regression, so this is building upon that. And as we get more into the course, it'll become gradually more difficult, but I'll do my best to simplify it for you. So just go on ahead to the next slide, and please sign in, by the way. All right, so again, these are our ML lectures. Education lead Alvin. I don't believe the other ML lecturers are here today. Let's go to the next one. All right, so these are resources just to help you gain more information into machine learning, because obviously there's only so much you can learn from a workshop. So just to enhance your learning, these are some resources you could use. We have our previous YouTube videos uploaded to our YouTube channel, and we also have that tagged on our link tree, so that provides immediate access for you. And then we have the slides shared as well. And again, as mentioned before, the difficulty of the concepts will gradually ramp up. We'll try to make it as approachable to a beginner as possible. And you guys can always interrupt me, feel free. Right, so this is the review of the previous lecture, which was centered on linear regression. So there's two really important concepts in machine learning: regression and classification. So what is regression? Regression essentially has to do with predicting continuous values. So when I say continuous values, we have two types of data: qualitative data and quantitative data. So qualitative data is data that we want to apply classifications for or labels for. So you can't add a number or tag a number to that data. So let's say I either pass a test or don't pass a test. I either pass a test or don't. I either pass a test or don't pass a test. So I can't assign a number to whether I pass a test or not, unlike quantitative data. So examples of quantitative data would be the GPA of a student or the height of individuals within a certain region. So you can actually assign a number to that data. You can say that your GPA is 3.6, 3.7, and so on. So that's what I mean when I say quantitative data. On the other hand, classification has to do with qualitative data. So again, that's classification, assigning labels to things, as opposed to regression. Regression is quantitative data, and classification is qualitative data. And both of these components fall under a concept called supervised learning. So what is supervised learning? Supervised learning has to deal with label data. So when I say label data, I mean data that we already have the answers for. So let's say I had the height of a certain population. We already have the heights for each person within that population or that sample we're using. So that's what we're referring to when we say supervised learning. And the goal in supervised learning is to implement loss functions. So what a loss function is we want to measure how wrong our predictions are, because if we know how wrong our predictions are, that allows us to improve our predictions and be more effective. So again, we can see this in real time as well with large language models like ChatGPT. We have ChatGPT 3, and then we went to 4, and now we're at 5. And it's constantly improving because it's learning from its mistakes. It's iterating, right? And as you see, we have two graphs here, one catered to regression and one catered to classification. So when you look at the regression graph, you see a line with blue dots around it. So those blue dots are all your data entries. And the more effective your data is, the more those dots are going to be closer to that line, that linear line. The farther it is, the more inaccurate your data is going to be, or the more inaccurate your predictions are going to be exact. On the other hand, we have on the right classification, where you have a division line, and then on the top you have circles, and on the bottom you have squares. So that's where we're implementing classification. We're either classifying the data entries as squares or circles. So if it's a square, it goes on top. If it's a circle, it goes on top. If it's a square, it goes on bottom. So that has to do with classification. So a fun way to think about it is regression is essentially guessing the amount of jelly beans in a jar. So you're quantifying that data, going back to quantitative data. And classification is predicting whether the things in the jar in the first place are jelly beans or something else like gummy bears. So that has to do with labeled data. So a common question we have is, can regression be used for classification problems? And yes, you can use regression for classification problems, but this has to do, you have to implement this indirectly. Because with classifications, you don't have numbers, you don't have quantities, right? So you want to apply a threshold. For example, let's say I either pass a test or fail a test. You want to assign a probability to me passing the test and a probability to me failing the test. So let's say I have a 0.8 or 80% chance of passing the test. That's my probability for passing. And then, of course, 1 minus 0.8, 20% for me failing. And again, how do you choose whether you use regression or classification? Well, you look at your output variable, so the number that the model is spitting out as your prediction. If that's a number, something that's quantifiable, we use regression. If that's a classification or a label, like mentioned before, we use classification. And we minimize a loss function in both because we want to know how far our predictions are from the actual answer, just so we can be as efficient as possible and continuously improve our models. All right, and now let's dive into one of the most fundamental concepts in machine learning, referred to as linear regression. So the formula, as tagged over here, is y hat equals wx plus b. And if you guys observe this formula, you can see that it mimics a formula that we're already quite familiar with. The equation for a line, y equals mx plus b, where of course m is your slope and b is your y-intercept. And your y hat is your model's prediction. So what your model is guessing, essentially. So linear regression at its core is trying to find the best fitting line through the data points that you're given. So when you plug in an x value, you get a y value, and you want that to be as close to the truth as possible. So in the example we have here, we have y hat equals 2.3x minus 20, and we have that x equals 70 and y hat equals 144. So how you get 144 is, of course, by plugging in 70 into the equation. And what we're doing here is our model is predicting that the value is 141. So this value isn't de facto. It isn't set in stone. This is just a guess or an estimate for what the actual value could be. Because again, we're using these models to predict values. But there's a catch to this. When you have data in real life, it's often messy. It constantly fluctuates and it's never uniform. So that's why we have to judge which line is best when we evaluate multiple lines. Which line is closest to the data points that we have. And how we do this is by using something called the mean squared error, also called MSE. So that's the formula for MSE there, where y sub I is your actual value and y hat sub I is your predicted value. So if you take the summation of this will give you your mean squared error. And the easiest way to think about your mean squared error is how far our predictions are from the actual data points, right? So we're looking at that difference between the truth and what our guess is. So we have this formula here. And then if you look at the graph on the right, you see residuals, you see predictions versus actuals. And on the right, you have residuals. So how you comprehend these predictions versus actual is we want the points that are hugging the diagonal line to be known as those that are closest to the truth. So those are our most efficient predictions, and the ones that are farther from it are less accurate. and we can fine tune our model to make those closer to the line. So there's not an actual line here, but if you can imagine a line, it's going up like a slope. And a quick analogy for this is, let's say you're playing darts and you want to hit the bullseye. Well, it's unlikely that you'll hit the bullseye first try, second try, or even a number of tries. But you constantly want to get closer to that center, and you constantly want to practice getting the bullseye. So that's what linear regression is doing. It's trying to become as efficient as possible. And when I meant, yeah.
What did you say the residuals graph is like representing here?
So the residuals graph is basically how inaccurate the data is here.
Oh, okay.
Yeah. So that just helps to keep it in view. Just because it's all over the place, we want it to be more compact and concentrated. And when you say fine-tuning the values, what I mean by that is you have the formula y hat equals wx plus b. So you can try playing around with the slope and the y-intercept just to make your model as efficient as possible. So a few common questions we have is, why do we square the errors and mean squared errors instead of just taking the absolute value? So we have to square the errors because this makes sure that whatever positive and negative errors we have, they don't cancel out, right? And also makes sure that the larger the error is, the more it's penalized, the more it's recognized that that is not supposed to happen as compared to the smaller errors. So we want to essentially prioritize the bigger errors and then move on to the smaller errors to make our model as efficient as possible. And another question is, what happens if the data isn't linear? Because in this case, all of our data is linear. We have that function, y hat equals wx plus b, which mimics y equals mx plus b. So if it isn't linear, it won't capture the relationship well, and you can't really use linear regression for this. So we might use other types of regression for data that isn't necessarily linear. So a few examples of this might be polynomial regression, for example, or other more flexible models that can accommodate for that data. Let's go to the next one. So why does linear regression fail for classification? Because as we mentioned before, we had regression and classification. Regression is quantitative data, and classification is qualitative data. So the reason you can't use regression for classification is because regression can give you an output or a prediction of any number. So for example, you might plug in any input into a linear regression model, and it might give you outputs such as -2, for instance, or 3.14, or 2.7, or anything of that sort. So let's say a common question is, what is the probability that the student passes an exam, right? And if the linear regression model gives you 2.7, that doesn't really make sense because you don't have a 270% chance of passing the exam. At most, you have a 100% chance of passing the exam. So you want your probabilities to fall between 0 and 1. It can't be outside of that. So the problem with linear regression is essentially that the outputs that you're getting is unbounded. It could be over 1, it could be below 0, and that wouldn't be efficient or even work for our model, first of all. So this is why we need to use a bounded function, and that comes to this bounded function, sigmoid. So the sigmoid function is a bounded function that's essentially used to crunch our data. So whatever input you give, let's say I give it 100, for example, it'll crush that data so it becomes a value between 0 and 1. Because if that value is between 0 and 1, then we can interpret it, right? Because let's say I plugged in 100 and gave me 0.6, that's a 60% chance. That's between 0 and 100%. We can actually make sense of that. It wouldn't make sense to say 300% or 500%, because those are just numbers at that point. It doesn't make sense in this context. And this is precisely where logistic regression comes in. So instead of drawing a straight line through all of your data points, as we saw in linear regression, and as we see in this graph to the right, we're essentially classifying data, and we're using the sigmoid curve, or the sigmoid function, to separate the categories. So as we see in the graph, we have pumpkin sizes. Let's say the pumpkin size is 10 and the prediction for that is 23.5. Well, that doesn't make sense because 23.5 in percentage is 2,350%. Again, we can't interpret it that. That's why you use the sigmoid function. We say that the pumpkin size is 10, and the probability that this pumpkin is orange, as seen in the graph, is 0.3. So one of the main benefits, first of all, of logistic regression over linear regression is that it gives us calibrated possibilities or probabilities as mentioned before. So it's not really saying yes or no, it's giving you a possibility or a probability for that yes or no. So there's a, for example, 60% chance of me getting a yes and a 40% chance of me getting a no. So that's more precise. We can actually use that in our models now because we can interpret it. All right, so some common questions we have here are, why can't we just make the linear regression values or the outputs between 0 and 1? And why we can't do that is because the nature of a linear regression model gives you unbounded values. It assumes a straight line, but it doesn't capture the S-shaped probability curve that we see in classification. So as we look on the right graph, it sort of resembles the letter S if you look at it. So we're not getting that here with the linear graph because it's just a straight line. So that's why we would favor logistic regression over linear regression. And again, as mentioned before, the main way we do that is by assessing our data. Can it be classified or can it be quantified? And why don't we use another function instead of the sigmoid function? So the reason we prefer the sigmoid function usually is because the sigmoid function is a smooth differentiable function, and it's easy to implement in this case. But we can use other functions, as we'll see later on these slides. An example of a certain function would be a softmax function, for example. And that would be used for multi-class classification. So we'll elaborate on multi-class classification later on in the slides. All right, now we're diving into the specifics of the sigmoid function. So as mentioned before, the sigmoid function is a function that bounds values between 0 and 1 so we can make sense of it. So the easiest way to think of it to make it stick in your mind is that it squashes the values, right, between 0 and 1. So let's say if our z value was 2, then our sigmoid function gives us a value of 0.88. So that's a value we can actually graph and make sense with. And for the sigmoid function, the larger your value is, it'll get squished to 1. So let's say my input was 100, for example. It would get squished to the value 1. If it was a negative 100, for example, it would get squished to 0. And if it was something in between, let's say 50, it would get squished to 0.5, which is our halfway mark. So if you look at the graph provided here, again, it's in the form of an S shape. So on the far left, on the left-hand side, everything is squished towards 0, and everything is squished towards 1 on the right-hand side. And in the middle, you have that fluctuation that gets you from 0 to 1. So a quick analogy to better picture this or visualize this is, let's say you had a switch to turn on and turn off your lights. If I turn it completely to the right, it turns on completely. So that's your value 1, essentially. And if I turn it completely to the left, the lights turn off completely. So that's your value 0. But if I do it somewhere in the middle, the lights still turn on, but they may not be as bright as when you turn it on fully. So it might be dim, and that's why your output value would be somewhere around 0.5. So a few common questions we have for the sigmoid function specifically is, why do we need the sigmoid function instead of rounding the output? Because if you just rounded the raw values, we'd lose the notion of probability itself. So you won't be as accurate if you're just rounding the values. Instead, you want to use the sigmoid function to be as precise as possible. And what happens if the input is exactly 0? So a common thing to note in the sigmoid function is that if the input is 0, your output value will be exactly 0.5 or halfway between. Let's move ahead to the logistic regression model. So this is the main crux of today's presentation. Everything before that was more so review. So how you implement or compute the logistic regression model is pretty simple. It's actually quite similar to the linear regression model, bar a few steps onto that. So your first step would be computing the score using the formula we're familiar with. Y hat equals W times X plus B, where W is your slope and B is your y-intercept. And whatever value you get when you plug it into Y hat equals WX plus B, that's our Z value. So once we get that Z value, we can plug that Z value into our sigmoid function to crunch or bound that value so we get the probability that it's between 0 or 1. So we have an example here. Let's say our weight is 0.1 and our B is -7. And for some input we decide to implement, our Z value is 0.5. So if you plug it into this function, you ultimately get 0.62. So you have a 62% probability that it belongs to the positive class. So when I say positive class, I mean that if the value or the output value is over 0.5, you want to call it the positive class. And if it's below 0.5, you want to call it the negative class. And that point where it's at the 0.5, that's essentially called your decision boundary. So your values are usually above that decision boundary or below that decision boundary. And we have an image or visualization here where you have map data, which is categorized in terms of low probability, which stands for green, and high probability, that stands for red. So logistic regression is mapping this data across, and you can see the difference between low probability and the high probability. And the high probability would just be a higher value on our sigmoid function, whereas the low probability or the green values would just be a lower value, below 0.5. So a few common questions we have for the logistic regression model specifically is, why did we make the decision boundary 0.5 instead of some other number? And the easiest way to answer that is just because 0.5 is exactly the midpoint between 0 and 1, which are the bounds for our probability, the upper bound being 1 and the lower bound being 0. And what happens if we change the threshold from 0.5 to something else? Well, if you change that threshold or the decision boundary, that changes the sensitivity of your model. So if you lowered the decision boundary from 0.5, for example, to 0.3, that would mean that the model predicts more positive values because more values would be above 0.3 rather than below 0.3. Similarly, if you made the decision boundary 0.8, for example, instead of 0.5, you're going to get more negative values just because there's going to be more values below 0.8 than above 0.8. And an easy way to visualize this is, let's say you have a weather forecast, right? It says you have a 62% chance of rain tomorrow. Well, because there's a 62% chance of rain, you want to use your intuition. You might bring an umbrella to avoid that rain. Logistic regression works the same way. It's not really saying whether it will rain or it won't rain. It's assigning probabilities to whether it will rain and whether it won't rain. So a few common questions with the logistic regression model specifically is, why can't we just stop at the linear equation y hat equals wx plus b, and why do we need the sigmoid? Because if you only use the linear equation, which we have here, y hat equals wx plus b, the problem with that is that, as mentioned before, it can give you any number. But we don't want any number. We want it to be bounded between 0 and 1. So that's a really important concept when it comes to logistic regression, and particularly the sigmoid function. We want to crunch our values. All right, and now we have log odds. So this might be a little confusing, but logistic regression, what we're doing in logistic regression is actually classification. So if anyone's wondering why we call it logistic regression in the first place, the reason we're calling it logistic regression specifically is because what we're doing is we're regressing on the log odds of the probability. And when I mean the log odds of the probability, I mean the odds of an event happening. So you want to note the differentiation between odds and probability, because they might sound the same, but they're not the same. An example of probability is, what fraction of times does this happen out of all the possible times? Or let's say I had an 8-slice pizza and I ate 3 slices. That would be a 3/8 probability. Odds, on the other hand, are how many times does it happen compared to how many times it doesn't. So I go out to play pickleball 5 times, but I don't go out 6 times, for example. Those are our odds. So we have the example here where p is 0.8. And in this context, that means that we have an 80% chance of success, right? So that means we have 20% chance of failure. And if you want to calculate the odds, you would just plug it into this log odds model. So if you plugged in p as 0.8, you would ultimately get 4. So that means that the event is 4 times more likely to happen than for it to not happen. And logistic regression doesn't calculate the odds specifically, it calculates the logarithms of the odds. So it's important to note that. That's why in this function we have log of p divided by 1 minus p rather than just p over 1 minus p. And the reason we're using logs is because we want to be more precise with our values. So when you take a log of 0.8, which is 1.386, the odds range from 0 to infinity. So I can say that the odds that I go somewhere are 10,000, for example. So those are really large values. And the reason we take a log is that it transforms this scale into something that's between negative infinity to positive infinity, and that's more easier to handle. So we have 3 graphs here: probability, odds, and probability again. So on the left, you see that how the odds approach or blow up, so it's going exponentially higher as it approaches 1. So this is why we don't want raw odds, and instead we want log odds, as seen in the graph all the way to the right. The second graph, you see how the log of the odds smooths things out into a nice linear looking scale here. And in the third graph, you see how we have the log odds, where the probability is 0.5, because it's between the middle. So the log odds are 0 in this case. And again, when we talked about 0, we know that 0 is our decision boundary. And an easy analogy to think of this is, think about sports betting. If a certain team, let's say a basketball team, has a 75% chance of winning, that means they have a 25% chance of losing. That means that they're favored 3-1. That means for every 1 time they lose, they win 3 times, right? That's odds in this case. But the reason we're using log odds is because it makes the math easier, and we can actually use it in the sigmoid function that we have. So a few common questions we have with log odds are, why do we need to use log odds instead of just doing the probabilities directly? Because the probabilities are between 0 and 1, as mentioned before. And that's tricky for linear models. But log odds make it into negative infinity to positive infinity, which is better for regression. Because for a classification, that's not the case. But for regression, when you have quantifiable data, you want that spread of data. So you want it between negative infinity to positive infinity. And why does a log odds value, what does a log odds value of 0 mean? So if the log odds value is 0, that means that the odds are 1. And as mentioned before, 0.5, which is your decision boundary. Let's move on to the next slide. All right, we have cross-entropy loss. So we figured out how logistic regression produces the probabilities, but what we really want to figure out is, how does the model learn? How does it build upon its past mistakes, and how does it constantly improve? So how we're improving that is by the introduction of loss functions. So when I say loss function, as mentioned before, a loss function tells you how often an error happens. So if you know how often an error happens, you can tweak the settings or tweak the parameters of your model to make it so that you aren't getting losses or errors as often. Because errors are bound to come, but you just want to limit the rate of the errors just to be more efficient. So let's say you have a situation where the model predicts the possibility no with a 99% probability. That's a confident mistake, because your error is at a 99% possibility, and you don't want that, because that's an extremely high possibility that your data or prediction is wrong. So we want to eliminate those large errors. And the most common form of a loss function we have is the cross-entropy function, as mentioned here. So again, cross-entropy isn't deciding whether a certain model is right or wrong, pass or fail. It's more so deciding how confident that model was in its mistakes. So the formula might look a little intimidating, but let's try to break it down. So if your true label is 1, we look at the log of the predicted probability. If the label is 0, we look at the log of 1 minus the probability. And then we average this across all the samples. So that's where you get the summation, just so you can average it across all the samples to make it work for all of your data points. So if you look on the graph, you have logistic regression in action. You have class 0 points, which are red. The red points sit at the bottom, and the green points sit all the way at the top, which is at 1 probability. So if y equals 1, but the model predicts 0.01, the loss in this case, if you plugged it into the function, would be approximately 4.6. And that's a confident error, and we don't want confident errors because we want to eliminate the rate at which we get errors in the first place. So this is specifically why we train utilizing cross-entropy, just to eliminate the rate of our errors and be as efficient as possible, because that's the ultimate goal of a model, to make your predictions or guesses as accurate as possible. So a few common questions we have for cross-entropy loss is, why don't we just use mean squared error or MSE like in linear regression? Well, the problem is that MSE works for linear regression, but it doesn't handle the confidence of errors. So it can't tell you how often something is bound to go wrong and how often something is bound to go correct, which is exactly why we use cross-entropy. It gives you the chance that something is right and the chance something is wrong. And it's essentially punishing errors that have a high percentage of happening. So let's say I had a 90% chance of something going wrong. We want to eliminate that, because in real life situations, we can't risk having that. Let's say we had like Tesla auto driving software. We can't really have errors because that's at the cost of lives. So we want to make it as efficient as possible to limit any damage. And why does cross-entropy use logs in the first place? Well, the log function grows sharply as the probabilities get close to 0. And that really points out the confidence of the mistakes, just so it's easier for you to see and improve upon. Let's go to gradients. All right, so now we've talked about how we measure the confidence of the errors, or how often a certain error happens. But how do we actually fix those errors? Because it's not enough to point out that something is going wrong 90% of the time or 80% of the time. We actually want to fix that to make our model better. And this is where the concept of gradients comes in. So in the context of machine learning, gradients is essentially your steepest downhill slope of our error function. Like, let's say you were standing on a mountain, for instance. If you want to get to the lowest point as fast as possible, you don't wander randomly. You take a straight path, or the most optimal path. And this is what our gradient function gives us. It gives us the most optimal path to improve upon our mistakes. So we have these functions here, where P is the predicted probability, Y is your true label, and X is your input. So what this essentially means is that if your model is consistently over-predicting or under-predicting, so it's either going higher than the true value or way lower than the true value, you don't want that to happen. And the gradient function shows you when that's happening, so you can actually address it real time. And that tells you how to tune your parameters as well. So if you look at the diagram on the right, we have a loss function here, which tells us how much of the error we have, and that depends on our weight values as well. So on the top of our graph, our weights are high, our errors are high. So that's a really bad guess at a high probability. And the lower we go, the lower the probability or the confidence of our errors, which is good. So we don't want it to be high, we want it to be low. So a few common questions we have when it comes to gradients is, why do we take the average 1 over n, as you see here? because it says 1 over n summation of p minus y times x. So where did we get that 1 over n from? So we get that 1 over n because in real life situations, when you're working with data and you're manipulating data, you're doing it in terms of batches, entire batches of data. You aren't just taking one sample of data and making predictions on that. So when you're taking batches of data, you want to average it using 1 over n. So whatever prediction you get, it represents the overall data set and not just one example. Because if it was just one sample or one example, that data would be biased, and we don't want that for our prediction. And why is it called the steepest downhill direction? That's just because the gradient points in whichever direction the loss is the fastest. So it doesn't necessarily have to be from left to right, it could be right to left as well, as we see with the parabola. All right, let's move on to optimization. So now we know what the gradients are. We know how we can improve our mistakes to make our model as efficient as possible. But now we need to figure out how to update the model. Because the gradients showed us how to update the model, we need to actually implement the upgrades or the optimizations itself. This is where we have optimization. The main tool we use in optimization is something called gradient descent. And what gradient descent, as we mentioned before, gradients is the steepest downhill direction. So what a gradient descent is basically saying is that we want to take a small step in that direction to reduce the loss. Because if our y value or our output value is getting smaller, that means that the confidence of our error becomes smaller. And that's what we want. We don't want our confidence to be high. And if you look at the graph, that letter A, that's referred to as alpha, and that's your learning rate. So it determines how big our steps are and how much we're changing by. So it's essentially, you want to think of it as slope in y equals mx plus b, how much we're altering our values by. And the problem is that if A or alpha is too high, we take steps that are really big, and that means that we skip over the data. And that causes divergence because we're going across so many values and we're skipping so many values, we're not accounting for the total data set. The problem if you go too low is, on the other hand, it takes really long to go through and comb all that data, and we don't necessarily need to go through every data point in our sample. We want to be uniform with it so we can be efficient and accurate. And on the right-hand side, you see two rules. One of them is the standard gradient descent update rule, so how you update your gradient learning times. And the second one is your momentum-based update rule. So this one refers to the past updates as well. So a simple analogy to think of this is if you're trying to find your way to the bottom of a valley at night with only a flashlight, the gradient is your flashlight because it points you to that direction that you want to take to optimize your model. And the learning rate is the size of your steps. You're either taking long strides to get to your destination, or you're taking short, frequent steps to get to your destination. And if you take too big of steps, you might lose your way. You might fall off a cliff, for example, just because you walked too much or you took a bigger stride than was necessary. And the opposite happens if you took smaller, more frequent steps. It would take way longer to get to your destination. You might become tired and you might not even reach your destination in the first place. So a few common questions when it comes to optimization is, how do we choose the learning rate? So how do we get that value alpha to plug into our function? So the reason, or how we get alpha specifically, is we do experiments on our data, or we fine-tune our data. So some data samples or some data batches need smaller learning rates to be as efficient and accurate as possible, where other data, which are really large, can handle larger strides, just because the data is just so large. It might be in the billions, for example. And what happens if we don't use a learning rate? So let's say alpha is 0 in this case. That means we don't update the weights and that the model isn't really learning from its past mistakes. So if alpha is 0, that's detrimental to our model because we're not improving. And we constantly want to improve our model and make it learn from its past mistakes by itself. All right, let's go on to decision boundaries. So as mentioned before, when you have classification, you have decision boundaries. So decision boundaries are essentially using labels. So if it belongs to a certain group, it goes on the top in the green section, for example. And if it belongs to another group, it goes on the red section, for example. So you want to think of your decision boundary as a tipping point. It's a 50-50 uncertainty. So if it's above that 50%, it goes on the top. If it's below that 50%, it goes on the bottom. So if you look on this graph, we have the default values, and then we have the repay values. And that linear line here, that's exactly our decision boundary. So when you have a two-dimensional plane like this, you just call it a plane, but in higher dimensions, you refer to it as a hyperplane. And it's really hard to picture things in 4D or higher dimensions, for example, but you can represent it by a map. And that's why we refer to it as a hyperplane. So if you look at the graph, the x-axis represents income, y-axis represents employment duration. The red point represents people who defaulted on a loan, and then the green represents people who actually repaid their loan, right? So at its core, the decision boundary isn't really about separating classes. It's about providing thresholds. So if it's above 50, it goes into one group, and if it goes below 50, it goes into another group. So a few common questions we have with decision boundaries is, why is the boundary, again, as mentioned before, 0.5? Because that's the natural midpoint. And can decision boundaries ever be curved instead of a straight line as we see here? So decision boundaries can be curved, and in simple logistic regression, the boundary is linear. But as you get more complex, and if you're doing regressions such as polynomial regression, for example, you would want your decision boundary to be curved instead of linear. All right. Let's move on to evaluation metrics. So now that we've built and actually trained our model and improved upon our mistakes, how do we know that if we actually efficiently improved our model? How do we know if our model is good after we attempted to improve it? Because we did what we could to improve it, but you actually want to evaluate whether that worked or not. So this is specifically where evaluation metrics come into play, and these help you decide whether your model has actually improved or has actually done the opposite. It's actually gotten worse, which you don't want to happen. So one of the tools we use is something called a confusion matrix. And a confusion matrix breaks down our predictions or guesses that the model gives us into 4 groups. So our first group is true positives. So when I say true positive, a true positive is the probability that the model predicted yes, and it was actually yes. A true negative was the probability that, let's say I predicted no and it was actually no. And a false positive is, let's say I predicted yes, but it was actually no. False negative is, I predicted no, but it was actually yes. So these are really important because let's say you had a medical illness, for example. You can't just say that you either have cancer and then have it not be true, because that's detrimental. So those are where your confusion matrix come into play. We have other metrics as well when it comes to our evaluation metrics, such as accuracy. So accuracy refers to what % of our predictions were actually right. Precision, on the other hand, is how often did it predict a certain value. So it's not how often we got it right or wrong, how often it predicted or gave out a certain value specifically. And recall is how often did it catch certain values. So to elaborate on recall, it's essentially if you're saying out of all the actual yes cases, how many did the model actually catch? So if there were 12 yes cases, for example, and I only caught 6, I would only catch 50% of that. And we would want to improve that to maybe even get 100% accuracy. So precision, if you want to think of it in terms of an anecdote, is of the number of fish you got, how many were the right type of fish? Recall is of all the fish in the pond, how many did you manage to catch in that pond? And then we have F-scores, which is your function. which you can calculate via 2 times precision times recall over precision plus recall. All right, let's move on to regularization. Yeah.
What did F1 stand for?
Yeah. So F1 essentially balances both the precision and recall that you have. So it's combining both of them to give your F1 value. Here we have regularization. So when do you want to use regularization in the first place? What type of situation mandates its use? So sometimes when you have a model that gets too good at learning the data, it starts memorizing the data instead of actually predicting the values based on past data. And you don't want it to memorize the data because then that problem is called overfitting. You don't want to overfit the data. So how you want to imagine it is, let's say you gave students the answers to last year's exams and they memorize every question and every answer perfectly. And when you gave them a slightly different test, they fail. And that's because they didn't actually learn the concepts. They just regurgitated what the previous test answers were. So they're not learning things, they're memorizing it. And regularization in its core is you don't want to make your model too complex. At its very core, you want it to be as simple as possible to limit as many errors as possible and to avoid overfitting. So we have the function Lreg equals L plus lambda over 2, absolute value of W squared, where L is your original loss, which is similar to cross entropy. Your lambda is your regularization strength, so the strength at which that's happening, or the rate at which that's happening. It's similar to alpha in that sense. And W squared means that we're penalizing large weights. So again, we want to eliminate confident errors. We want to reduce our rate of errors to be as efficient as possible. So now our model has two goals. We want to fit the data well, and we want to keep the weights small. Because the larger our weights get, the more likely that our data or predictions may not be as accurate to the actual truth. Now there's two types of regularization. We have L1 and L2. L2 regularization is also called ridge regularization. And this shrinks the weights smoothly towards 0, but it doesn't make them exactly 0. So it helps in keeping things stable. L1 regularization, on the other hand, which is also called lasso, pushes some weights to be exactly 0, which creates sparsity. So when it says pushes some weights to be exactly 0, an example of that might be it's pushing the large weights to 0 to make your data or your predictions more efficient. So an analogy to think of this is if you're packing for a trip, without regularization, you're packing everything, even things that you don't need. And that's really unnecessary. So what regularization is doing is that it's eliminating that overfitting. It's only giving you the things that you actually need for your trip. So that's making the model more optimal in that sense. All right. And here we have multi-class regression. So far when we talked about logistic regression and classification, we talked about it in a binary sense. So we have two labels. Either you passed a test or you failed a test. Either you got spam or you didn't get spam. Either it was default as seen in the graph before, or either you actually repaid your loan. But what happens in the instance that you have more than two categories? Because we need to account for that as well. Because in real-time data, you more often than not actually do have more categories. You have hundreds, thousands, millions of categories. So for example, if you're predicting which digit a handwritten number is, so the numbers are 0 through 9, and you also have another classification, if you're classifying something into a cat, dog, or a gator, for example, you're working with multiple classes, and this is where you want to use multi-class logistic regression. So there's two main approaches to logistic regression, which we won't really get into the specifics of, but these are nice to know from a general perspective. One approach is one versus rest, which is also referred to as OVR, where we train one classifier per class. So each classifier asks, is this, first of all, a class or not? And then, for example, in our example to classify the digits from 0 to 9, the model is asking, is this actually a 0? Is this actually a 1? And so on, until it gets to 9. Softmax regression, on the other hand, as we see through the formula here, is instead of building many classifiers, you want to extend the logistic regression directly to multiple classes. So you want to apply that logistic regression to all of the classes that you have in question. So the idea is pretty simple. We compute a score for each class, we apply the softmax function, and we interpreted the result as a probability distribution across all of the classes, so we can account for all of our predictions. So looking at this graph, what it actually means is that for each class, we're exponentiating its score. So Wx, that's where we get Wx plus b. And then we divide it by the sum of the exponentiated scores across all classes. That's where we have in the denominator the summation of all those exponential scores, because that gives us the total sum. And the result, again, is a probability between 0 and 1, because in logistic regression, you want your output values to be between 0 and 1. So let's say we're classifying an image of a handwritten 7. The softmax might output probabilities such as 0.02, for example, or 0.01 or 0.92. So they're all between 0 and 1. And if you add all those probabilities together, of course they equal 1, because that's your total probability. And let's say that the probability, as mentioned before, for the 0.92 was the number 7. That means that 7 is your most confident value. That means that it's guessing the 7 most right, if that makes sense. So softmax is essentially a voting system in the sense that each class is getting the score, and the higher the score that you get, the more confident that prediction is. So again, we want our predictions to be accurate. We don't want our errors to be accurate. So that's how you want to differentiate the two. All right, and thank you guys for this lecture on logistic regression. If you have any questions, you can come here, ask me. It's totally fine. And please sign in again if you haven't signed in. Thank you.